All right, so we want to try and classify certain types of vector fields. So a definition that we have, a vector field is called conservative if there exists a function, say little f, such that the vector function, capital F, equals the gradient of f. So the gradient being that vector valued function that contains the partial derivatives. If it does exist, then that function little f is called the potential function of the vector valued function f. So for example, we could try and look at this one here. So let's say the vector valued function f of xy equals the vector 3x squared comma y. We could try and think about, is this a conservative function or not? So does there exist some function where these are the partial derivatives, where the first one is the partial derivative with respect to x, and the second one is the partial derivative with respect to y. Well, this function is kind of simple enough that maybe we could just guess, right? Maybe we could just find it. So for example, try, let's say, little f of xy. Well, I need the x part to, like if I take the derivative with respect to x, that partial to just be 3x squared. So maybe we just have an x cubed component in here and no other x's. And then I need the y partial derivative to just be y. So maybe we just keep y completely separate and have it be something like y squared, except I have to bring the 2 down and get a coefficient of 1, so maybe y squared over 2. If we try that out, then we can see that then the partial derivative of f with respect to x is indeed that 3x squared, and the partial derivative of f with respect to y is indeed y. So the gradient of f does equal the capital F function. So the answer here would be yes, f is conservative, and little f is a potential function. So this isn't necessarily a great way to do that type of a question because we just kind of got lucky that we found it. So we're going to talk more later about how to find it. But the first question before we start to talk about how do you find a potential function is, well, are all vector fields conservative? Is there always a potential function, or does sometimes it not exist? And the answer is no, they're not all conservative. So then coming off of that, then our question becomes, well, how do I decide whether or not a vector field is conservative? So we have a first theorem, and this is going to be for plane vector fields, so two-dimensional. So we've got capital M and capital N. So these are going to be the two components of my vector field. So I've written it this time in linear combination of I and j form. So we've got capital F of xy equals m times I plus n times j. And we've got this extra restriction where m and n are both differentiable, so I can take their derivative again. The formula that we've got here, our condition, is that this vector field is conservative if and only if I take the partial derivative of m with respect to y, it's equal to the partial derivative of n with respect to x. Now, there's sort of this question of why is that true? Why does that mean that these are indeed a conservative vector field? Well, notice what we did is we flip-flopped things, right? The first one, the m component, we took the partial derivative with respect to y, and then the n component, which was the y component, we took the partial derivative with respect to x. Now, if we think about where those would have come from, if it was a conservative vector field, if it did come from a potential function, then the first component would have been a partial derivative with respect to x. And the second component would be a partial derivative with respect to y. So what really would have happened at this point then is we took a partial derivative with respect to x, and then took its partial again with respect to y, giving us one of the mixed partials. And then this n, if it is conservative, comes from a partial derivative with respect to y, and then we're taking the partial with respect to x of that, which gives us the other mixed partial. And so what we're using is that theorem that we talked about in the past, that mixed partials should be equal to one another for these functions. So it's true if and only if those derivatives are equal to one another. So what this is nice is what it does is it just gives us a way to check yes or no. It doesn't tell me what the potential function is if it exists, but it tells me whether or not it exists. So again, with that one that we just looked at before, obviously we already know it's conservative because we just got lucky, but let's see if we can use this formula to show it. So what we would do then is we're going to check, we're going to take this first one, this is our m, so we're going to take the partial of m with respect to y. So you do the opposite variable. So the first component is an x component, but we're going to take the derivative with respect to y. So we're taking the partial with respect to y of 3x squared. Now, if we think about that, well, there are no y's in that expression, so therefore the partial derivative with respect to y, we're really just differentiating a constant, so it's 0. Now let's try the other one. The second component is the n component. So we would have the partial of n. This time we do with respect to x, so we do the opposite variable. So this is then the partial of the value of y with respect to x, which again, with respect to x is constant, so this is also 0. So since those are equal, then yes, capital F is conservative. Let's look at a second example. So let's just look at something very similar, but just flip-flop the places. So instead, let's look at g is the vector valued function of y, comma 3x squared. Now again, m and n are fixed. So m is always the I component, which is the x component, and n is the j component, which is the y component. So this time the partial of m, we always do it with respect to y, so we do the I component with respect to y, would be the partial with respect to y of y, which is 1. And then if I look at the other one, the partial of n with respect to x is going to be the partial with respect to x of 3x squared, which that derivative is going to be 6x. And so what we have is these are not identically equal as functions. That's what we're really looking for, is as functions, are they equal to one another? So since not equal, so this vector field of G is not conservative. Which means it is not the gradient of any function. There's no function who has that as its gradient function. It's still a vector field, it's still a vector valued function, and we could create its graph and everything, but it's not, it doesn't fit in this category of vector fields. So what we're going to talk about in our next video is, okay, now that we can answer yes or no of whether it's conservative, if we did answer yes, how do we find the potential function without just guessing and checking?